Must every large set contain an arithmetic progression? This is a really old question in mathematics, and one that's led to a lot of beautiful ideas. In this video, I want to discuss 3 answers to this question that use very different ideas to reason about it. An arithmetic progression is 3 numbers of the type 10, 15, 20, or 7, 9, 11. Those are all examples of arithmetic progressions. In general, it's 3 numbers that are distinct and look like a plus b, a plus 2b. Or you can also think of it as 3 numbers that look like x, y, and the average of x and y. Okay. So what we want to understand is it possible to have a very large collection of numbers or objects that you can do arithmetic on and yet avoid arithmetic progressions? So here are the 3 statements that I want to prove about this. The first one says that there is a large set of numbers that avoids arithmetic progressions. In fact, it's a little bit stronger. It says that you can always color the numbers from 1 through n with a small number of colors, with 2 to the square root log n colors, in such a way that there will be no monochromatic arithmetic progression. Meaning that if you look at any 3 numbers like this, then one of the numbers will get a different color from the others. That's the first result. And this implies in particular that there will be a large set of numbers with no arithmetic progression, because you can take the color class here of largest size, and that color class will contain at least n times 2 to the minus square root log n colors in this coloring, and that set will contain no arithmetic progressions. So that's the first result I'll discuss, and this result just uses some simple intuition from geometry. The next result I'll talk about says that if you have for any constant delta, if you take n to be large enough, and you take delta n elements of this, delta n elements from the set 1, 2, 3 up to n, then you will be forced to contain an arithmetic progression. Okay. So this says that you will be forced to contain an arithmetic progression if you take sets of constant density. And this is again a really beautiful result. It uses many ideas from Fourier analysis. And the last result I'll discuss is this one, and it's about sets that live in a different algebra. So we'll be working over a vector space over the finite field F3. So these are the integers modulo 3. And so look at vectors with integer coordinates of length n, and look at these vectors modulo 3. Then the result says that there's some constant c that's less than 3, so that if you take c to the n elements from this space, then you will be forced to contain an arithmetic progression. And this last result uses ideas from linear algebra and polynomials to reason about this problem. So the reason I really like this problem is because it's a basic question, but to reason about it, there are all kinds of different ideas that seem to have leverage depending on what you want to show. So if you want to learn about this question, you end up learning a lot of nice ideas from different parts of mathematics. Okay, so let's get started. Let me start with the first result. Does every large set contain an arithmetic progression? The answer that we're going to give is no. For a set of a certain size, we're going to construct a large set with no arithmetic progression. And the intuition here is extremely simple. There is a setting in which we know it's easy to see that you can avoid a structure like x, y, and the average of x and y. And that is if you think about the points on the surface of a ball, the points on a sphere. Okay, if you take 3 points on the on the sphere, on the surface of the ball, then they cannot look like x, y, and the average of x and y. Because if x and y lie on the surface, then their average will lie inside the ball. Okay, just like in this picture. So that says something about vectors. Okay, you can avoid, you can find lots of vectors that avoid the structure of arithmetic progressions. But we want to find sets of integers that avoid the arithmetic progressions. And how can we do that? Well, the idea is to associate with every integer a vector. And we'll do it by writing the integer in DOE representation for some choice of D. Okay. So we'll take any integer from 1 through n. You can write it as a vector where the coordinates of the vector correspond to the digits of the integer when it's written in DOE representation. And we'll choose this capital D so that it's roughly 2 to the square root log n. Okay, 2 to the squared log n. And if you think about it, then the number of digits you need to represent an element of 1 through n when capital D has this value is roughly square root log n. Okay, this is because d to the d, capital D to the little d, looks like 2 to the square root log n to the power squared log n. That's equal to 2 to the log n, which is equal to n. Okay. So when little d hits this value, you've had enough digits to represent all of the integers from 1 through n. So given this representation, the idea would be to try and color every element x, every integer x, from the set with the length of the vector corresponding to x. Okay. Then all of the vectors that have the same color will lie on the surface of the same ball. So that makes that's according to our intuition. So let us check first that the number of colors here is small. What can I say about the magnitude of the length of the vector of x? Well, that's equal to the sum over all the coordinates of the digits squared, but all of the digits here are at most capital D. So this is at most d times capital D squared. And if you look at our choice of parameters, this is at most 2 to the order square root log n. Okay, so the number of colors is small, as we promised. However, there's a bug in this argument. It doesn't quite work. And maybe it's a good time for you to pause the video and try to see if you can find the bug yourself. The bug is that this vector here is not the average of the two vectors. It's not equal to the average of the two vectors at the endpoints. In general, it's not always true that these two are equal. Okay, in fact, this vector could lie on the surface of the ball. That's because when you add numbers, there might be a carry bit in the DOE representation. There might be a carry digit that goes across. So addition of the integers here does not correspond to addition of the vectors. Okay. So there's a problem with this idea. And to fix that problem, we just need to modify this idea a little bit, and that's what I'll do next. Here's how we can modify the idea. I'm going to add some additional data to the coloring. Okay. For every x, I'll construct a vector that corresponds to an integer z. And what is this integer z? Z is obtained from x by rounding down the digits of x to the nearest multiple of d over 4. So zi here is obtained by taking the digit xi and rounding it down to the nearest multiple of d over 4. That's zi. So this gives you a new integer z, and we'll color x with first with the value of the vector representation of this new integer z. And in addition, we'll color x with the length of the vector x minus c, the vector of x minus c. So that's the fix to the old problem. And why is that a fix? Well, first, the number of colors does not increase by too much. The number of choices for z here is only 4 to the little d, because z can have at most 4 values for each of its digits. So there are 4 to the d choices for z, and the number of colors that we have from this part is at most 2 to the order squared log n, as we discussed before. And so the total number of colors again is 2 to the order squared log n by our choice of parameters. So the number of colors is still small. That's the first property. And now if you think about what's happening, if I have an arithmetic progression x, y, and the average of x and y, then and that arithmetic progression is monochromatic, meaning that all of x, y, and the average of x and y have the same value of z, have the same z value, then I obtain another monochromatic arithmetic progression, namely x minus z, x plus y over 2 minus z, and y minus z. This will also be an arithmetic progression. That's monochromatic. And these 3 numbers have the feature that all of their digits are small. All of their digits are at most d over 4. And that means the problem that we had before does not occur anymore. When you add 2 of these numbers, there is no carry digit. So addition in the space of integers corresponds to the addition of vectors. And the idea works. Okay. It's impossible to have a monochromatic arithmetic progression here because you cannot have 3 vectors that lie on a line like this and they're all on the surface of the same ball. So that's the first result, and it just uses a basic intuition that if 2 points lie on the surface of a ball, then their average has to lie inside the ball. Next, I'm going to show a result in the other direction, that if you have a large set of numbers, then it must contain an arithmetic progression. And here the setting, here what I'll show is that for every constant delta, if n is large enough, then if you take delta n elements from the set 1, 2, 3 up to n, you will be forced to include an arithmetic progression. This proof uses Fourier analysis. The structure of the proof will be that we'll use Fourier analysis to show that if you start with a set that violates this theorem, if you find a set that's free of arithmetic progressions and it's of size delta n, then you can obtain from it another set that has even larger density. The density of this initial set was delta. The new set we'll find will have density delta plus something like delta squared over 100. And this new set will also not have any arithmetic progressions. And that shows that this initial set S could not have existed, because if you can from S obtain the set Q with a higher density, you can repeat the argument again. From Q you can obtain another set with even higher density. And if you repeat this argument something like 100 over delta squared times, you will eventually obtain a set whose density exceeds 1. And that's not possible. Okay, that's not possible. So it's enough to show that starting from a set that's free of arithmetic progressions of size of density delta, you can obtain an even more dense set that's free of arithmetic progressions. And that's what we'll do. And to do this, we'll use Fourier analysis. I'm not going to review in detail the proofs for statements of Fourier analysis that we'll need. I'll just write them out here. If you're not familiar with these ideas, then you should look them up and review them before continuing. So we're going to be doing Fourier analysis over the finite field Fp, where p is a prime number. So let p be some prime number. Then we'll be working over the integers modulo p. And over this set, some basic facts are that for every element of this set that's non-zero, I should write non-zero here, there exists an inverse such that k times k inverse is equal to 1. Okay, there's a multiplicative inverse. That's the first fact. And if you take omega to be a primitive pth root of unity, this is a complex number which is a pth root of unity on the unit circle, then basic fact is the expected value of omega to the power kx, where x is chosen randomly from the finite field, is equal to 1 exactly when k is equal to 0 in the finite field. Okay, otherwise, it's 0. And then the basic identity of Fourier analysis is that every function f from the finite field into the reals of the complex numbers can be expressed as a linear combination of omega to the kx for different values of k. Okay, so I can write it as a linear combination of omega to the kx, and the constants in the linear combination, these are the Fourier coefficients of the function. Now you can use this identity to prove that the Fourier coefficient f hat of k can be recovered by taking the inner product of f with omega to the minus kx. That's just a consequence of this and this. And you can also prove that the expected value of the magnitude squared of f of x is the sum of the squares of the Fourier coefficients. And that's also a consequence of, you can write this using this identity and this identity. You can prove this equality. Finally, we'll need the concept of convolution. The convolution of two functions f and g is given by this formula. Okay. And convolution behaves very nicely in the Fourier world. The Fourier coefficient of a convolved function of a convolution is equal to the product of the coefficients of the original functions. So now let's use Fourier analysis to reason about the problem we care about. So let's say we're given a set S of density delta n here, and we want to try to find an even denser set that's free of arithmetic progressions if S is free of arithmetic progressions. To do this, let's choose P to be a prime number between 4n and 2n. Okay, and then we can think of the numbers 1 through n as elements of the finite field Fp. And let's write 1s and 1n to denote the indicator functions for the sets s and 1 through n. And I think of these as functions mapping the finite field to real numbers. And I want to start by trying to understand the intersection of S with a long arithmetic progression T. Okay, so for some parameters T, K, and L here, I will construct an arithmetic progression that looks like T plus K, T plus 2K, all the way up to T plus LK. This is an arithmetic progression of length L. And I'm going to eventually choose T, K, and L to try and somehow capture a lot of the density of S. Okay, so I'll be interested in understanding the intersection of S with T and the density of this intersection. Okay, this will ultimately lead to the set Q that I promised earlier. Because if S is free of arithmetic progressions and S intersect T has high density within T, then I'll obtain basically a subset of 1, 2, 3 up to L that has higher density and is also free of arithmetic progressions. That's the idea. Okay, so let's not worry about too much about the constraints on the parameters right now. But eventually, it will turn out that I will set k to be a number between minus square root n and square root n, and L to be a number of the type epsilon times square root n, where epsilon is very small. Okay. We'll see how to set these parameters as we go. But the first thing I want to understand is how can we measure the density of T intersect S inside T? And the way to do this is, so we want to measure the density of T intersect S, and we want to make sure that this density is higher than delta. So I'm going to try to write down an expression for the size of T intersects S minus delta times the size of T intersect 1 through n. This is what I would like to say is large. Okay. And this expression has a nice form. Okay, using the formulas we defined above, because I can write this as a sum over x of 1s of x times 1t of x minus delta times 1n of x times 1t of x. And that's equal to x times 1s minus delta 1n. So I can think of a new function here, 1s minus delta 1n, evaluated at x, times 1t of x. And I'll call this new function f. The function f is the difference of 1s and delta 1n. Now, if you think about what's written here, what is 1t of x? It's equal to the sum over x, to 1L of minus k inverse t minus x. X belongs to the set T exactly when minus k inverse t minus x is a number between 1 and L. Okay, that's because if you look at what's happening at this quantity here is exactly the location of x in this arithmetic progression, and that location has to be a number between, it has to be 1, 2, 3 up to L. It has to be in that set. Okay, and that's really nice because this expression looks like a convolution. It's equal to the sum over x, well, p times the sum of over x, it's p times the convolution of f with g at t, where here g of x is the function 1L of minus k inverse x. So that's a function that f is being convolved with. Okay, so the size of this intersection now we've managed to express as a convolution of f with this function g. and I want to be able to set t and k and L. Well, L I've sort of already set, but I need to set t and k so that this quantity is large. I want to set it so that it's large. And let me show you how to reason about that. Let's try and actually first maximize the magnitude of this quantity. So let's try and bound the expectation over t of the convolution of f and g at t, its magnitude. The expected magnitude of the convolution is at least the expectation over t of the convolution times omega to the minus r t, where here r is any element from the finite field. Okay, this is just a triangle inequality. The magnitude here is always larger. Oh, let me take the magnitude here so that it makes sense. I'm just taking a linear combination of these terms with coefficients whose magnitude is at most 1. So I can only get something that's smaller than what's written on the left-hand side. And I can, this statement holds for every choice of r. But what I've written here is just a Fourier coefficient. Right? This is equal to the magnitude of the rth Fourier coefficient of the convolution. But because convolution plays nicely with Fourier analysis, that's equal to the magnitude of the Fourier coefficient of f at r times the magnitude of the Fourier coefficient of g at r. And I'm going to prove that actually the magnitude of this Fourier coefficient for an appropriate choice of k can be made large. It can be made it can be made omega L over p. And that will give the bound omega L over p times f hat r. The second observation here is that the expected value over t of the convolution evaluated at t is just 0. And that's because if you look at what we have here, or let me just write p here. This expression here is the sum of f over all the elements of t. So this expectation is just expectation over t of f at t plus k plus f at t plus 2k, and so on. But every one of these quantities has expected value 0, because t is a uniformly random element from the finite field. So each of these is uniformly random. And f has been chosen so that its expectation over the entire finite field is 0. Right? The sum over all the elements of the finite field of 1s is the same as the sum over all elements of delta times 1n. Okay. So this quantity is 0. And that means that now if you look at 1 and 2, what that implies is, maybe I'll multiply the first equation here by p. Then what I get is the expectation over t of the absolute value of the convolution at t plus the value of the convolution at t is at least omega L f hat r. Now, the point is that whenever this quantity here is negative, this sum is 0. And when it's positive, this sum is twice the number. So if this expectation is greater than or equal to this quantity, then there must be some choice of t, actually many choices of t, where the value is both positive and at least half of this value. Okay, right? At least there's one value of t where this quantity is positive and at least half of this value. Now, there are some problematic cases here that I need to take care of for my intuition to go through, which is that ultimately I want to find L elements where the density of S in those L elements is higher than before. So it's problematic if my set T goes outside of the first n elements. I want to make sure that T is contained in the first n elements. And some choices of T would lead to this capital T going outside of the first n elements. But the number of such choices is small. Okay? Because T can only lead to the set T going outside the first n elements if T is such that T plus Lk is near n, okay, near the boundary of n, to where it straddles, the gap between T and T plus Lk here is L times K, and L times K is bounded by epsilon times n. It's a small fraction of n. So the probability, the contribution from problematic T's here, the T's that go outside, to this expectation is at most order Lk divided by P, because this is the chance that you hit one of those problematic intervals for T. And if you do hit one of those problematic intervals, you could potentially contribute L. So this is an upper bound on the contribution from problematic T's that are near the boundary. But this is small. Okay, this is bounded by epsilon times L. Okay, so the overall contribution, the overall expectation is omega L times f hat R, and the contribution of problematic T's is epsilon times L. So if you choose epsilon to be much smaller than f hat R, then we will get a valid choice of T that is completely contained in 1 through n, where the density of the set will be larger than delta. This quantity will be positive, and the density will be larger than the delta. So that's the idea, and the increase in the density that we get is related to the value of the Fourier coefficient, right? As long as you have some large Fourier coefficient, then you get an increase in the density of the new set. To explain the intuition behind what's going on here, let me show you an example. So let's say that you have some set S, which induces the definition of f, which is 1s minus delta 1 n. And what I've shown here in pictures is the value of f of x times omega to the minus kx for different values of x. Okay. So for every x from the finite field, you get a complex number here like this. And the average of these complex numbers is the Fourier coefficient f hat of k. Okay. That's the average of these numbers. And what we are trying to find is an arithmetic progression where S has unusually large density. And intuitively, as you change the value of k, the red points are going to move in sort of a random way, and most of the time they'll be distributed uniformly around the circle. So f hat k will have a small magnitude. That's true most of the time. But once in a while you might get lucky. Okay. If you get lucky, you find a value of k, like this one, where f hat k is actually quite large in magnitude. And intuitively, when that happens, it's because there's a large interval on the circle, a large region, where the red points have unusually high density. There's a lot of red points with large magnitude. And this corresponds exactly to an arithmetic progression where the set S has high density. Next, let me show you how to pick k so that the Fourier coefficient g hat r is large, is at least L over p. So let me remind you, the g of x is equal to 1 L of minus k inverse x. And that means that g hat of r is equal to the expectation over x of g of x times omega to the minus rx. And now I'll do a change of variables. This is the same as the expectation over y of 1L y omega to the rk y. And here's the intuition, if I wasn't too worried about the size of k here, okay, I have to control the size of k because earlier, here we use the fact that k is small to make sure that the problematic case t's don't contribute too much, that we really get a proper arithmetic progression inside 1 through n. If I didn't care about the size of k, then I would set k to be r inverse. And this would make rk be 1 in the finite field. And these elements then would just be, omega, omega squared, omega cubed, and so on. And there's only L of them. There's a small number of them. So they'll all be concentrated near 1. And their average will be roughly L. Okay. So if I didn't have to worry about the size of k, this would be easy. Now I do have to worry about the size of k, but it's still okay by a choice of parameters. Because consider the set of numbers r, 2r, 3r, and so on, up to square root n(r). There are square root n numbers here. And this means by the pigeonhole principle, 2 of them must be close. There must be br and ar, so that br minus ar is at most p over square root n. P over square root n. Okay, and that means that you get b minus a times r is at most p over square root n, which is bounded by 4 square root n or something. So set k to be this b minus a. And now you see that r times k is a number whose magnitude is at most 4 times square root n. And that means r times k times L is at most 4 times epsilon n. So this thing is at most 4 epsilon n. And if you choose epsilon to be small enough, then all of these numbers lie close to 1, and they don't go very far from 1. So the average of these numbers will be the magnitude here will be at least omega L over p. So far what we've managed to show is that if you can find a single Fourier coefficient of f that's large, then we obtain a density increment for S. And so far we haven't used anything about arithmetic progressions. All of what we said is true for any set S. Now let me show you how to use arithmetic progressions to show that S actually must have, the F must have a Fourier coefficient that's large. Okay. So let's do that next. And so that's the claim that's written here. There is some non-zero R for which the Fourier coefficient F hat R is at least omega delta squared. And to do that, we studied this expression. So this is the expected number of arithmetic progressions when you pick a random arithmetic progression in the space. So pick x and y randomly from the finite field, and this function here is 1 exactly when x minus y, x, and x plus y all belong to the set S. Now, if the set S is free of arithmetic progressions, then the only way you can get a contribution in this expression, because x minus y, x, and x plus y do form an arithmetic progression. If x minus y, if the set S is free of arithmetic progressions, the only way you can get a contribution here is if y is 0 and x lies in the set S. And here it's crucial that we chose the prime p to be bigger than 2n, so there are no wraparound issues. There are no issues of wrapping around. Okay, there's no way to get a arithmetic progression here in the finite field Fp without also getting an arithmetic progression among the numbers 1 through n. Now, the contribution of this expression when y is equal to 0 is what's written here. Okay. When y is equal to 0, then with probability delta n over p, x will lie inside S, and then with probability 1 over p, y is equal to 0. So that's the contribution you should have if the set S is free of arithmetic progressions. On the other hand, because f is 1s minus delta 1n, we can express 1s as f plus delta 1n. So this is equal to this. And now we will study this expression using Fourier analysis. When you expand this expression, you will get 8 terms. Right? There are 2 terms here, 2 terms here, 2 terms here, and every choice of term from each part will give you a term in the expansion. And one of these terms contributes a lot. One of these terms looks like the expectation of delta 1, delta 1, delta 1. This term contributes a lot. It contributes omega of delta cubed. Okay, because it contributes whenever the points x, x minus y, x, and x plus y lie in the first n elements. Whenever that happens, it contributes delta cubed. And that happens with constant probability, with some constant probability. So that contributes a large quantity. And this quantity here, is much larger than this quantity. Right? Here, there's a p in the denominator, so that's a tiny quantity as n is getting large. And so it must be that the other terms here cancel out the contribution of this quantity. So let's understand how they can cancel out this quantity. So let's study one of the other terms here. Let's study the contribution of the expectation of f, f, f. And let's write it out in the Fourier basis. Okay, so in the Fourier representation. So this is the expectation of the sum over R1, f hat R1, times omega the minus R1, x minus y, times the sum over R2. Now I'm going to rewrite this. I'm going to multiply these 3 sums. When I multiply them out, what do I get? I get the expectation over And this expectation is over x and y. Right? And now it's easy to simplify this expression, because for any fixed value of r1, r2, r3, the expectation is 0 if this is non-zero, if r1 plus r2 plus r3 is non-zero. And it's 0 if r3 minus r1 is also non-zero. And if both these numbers here are 0, then the expectation of this part is exactly 1. Okay. So those considerations imply that this is exactly equal to the sum over r1. And now let's bound the magnitude of this. So if I want to bound the magnitude of these numbers, well, let's say that alpha is the largest Fourier coefficient. Okay, so let's say that alpha is equal to the maximum over r of f hat r. Then what's written here can be bounded by alpha times the magnitude of the sum over r1 of f hat r1 squared. And now we'll use Parseval's inequality, or the magnitude of this squared. This quantity is at most alpha times the expectation over x of f of x squared. So I claim that this quantity is at most order delta. And that's because, when x lands inside S, the magnitude of f of x can be as large as 1, or very close to 1. But that happens with probability at most order delta. And when x lands outside of S, the value of f of x is at most delta squared anyway. So this quantity is at most order alpha times delta. Okay? And so you see that in order for this term to cancel out the contribution of this term, alpha here has to be at least as large as, it has to be proportional to delta squared, as big as delta squared.
And note that by the choice of f, the Fourier coefficient f hat 0 is just 0. Okay, because f has expectation 0. So the maximum Fourier coefficient, the Fourier coefficient of maximum magnitude is not the 0th Fourier coefficient.
Okay. If alpha is much smaller than delta squared, then this term cannot cancel out this term. And the same thing happens for all of the other terms in this expansion. I talked about the case f, but if you look at f1, you can do the same thing. You might end up here with f hat r1 times 1 r1. You can use the Cauchy-Schwarz inequality to write it as the norm of f times the norm of 1, delta 1, and you will always only get a better conclusion than what we got here. I'll leave it to you to check that. Okay, so this guarantees that there will be a Fourier coefficient. The fact that there is no arithmetic progression guarantees that there will be a large Fourier coefficient. And that brings me to the final result that I want to talk about, which is this one. It says that there's a constant c such that every subset of f3 to the n of size c to the n must contain an arithmetic progression. And this result uses just basic algebra. So a basic fact is that every function from f3 to the n to f3 can be represented as a polynomial of degree at most 2 in each variable. It never makes sense to take a variable and cube it, because over the finite field f3, x1 cubed is equal to x1. Okay. And this is pretty much the only fact I'll use, along with some linear algebra. So I can think of, let me write P P of D to be the subspace of all polynomials of degree at most D. Okay. This is a subspace I'll work with. And suppose you give me a set S that's a subspace of F3 to the n that has no arithmetic progressions. It does not have three vectors x, y, and the average of x and y all contained in the set. Then it must be the case that if I look at the set 2S, which is all elements of the type 2z where z is in S, and S plus S, which is the set of elements x plus y where x and y belong to S, then these two sets must be disjoint. Okay. Because if some 2z was equal to x plus y, then x, z, and y would form an arithmetic progression. So these two sets must be disjoint. And that means that if I consider the subspace V, which is the space of all polynomials for which g of x is 0 whenever x, this should be x, okay, whenever x is not in 2S, so this is a subspace, then this subspace must have large dimension. Its dimension must be the dimension of the original, the space of all polynomials, minus 3 to the n minus 2s, because these are the number of constraints that I'm adding here. These are the number of additional constraints I'm adding to the subspace. Okay. So the dimension of this V is large. And as a consequence, I must get, just from Gaussian elimination, if you think about it, if you have a subspace of dimension k, then there must be some some element of the subspace which has k non-zero coordinates. This is a basic fact from linear algebra that I'll leave to you to prove. So this means there must be a polynomial p in the subspace of dimension of degree d such that it is non-zero on the dimension of v number of inputs, and then the non-zero inputs, they correspond to a set T that's a subset of 2S. Okay. Because on all the elements that are outside of 2S, the polynomial p must be 0. So the set of non-zero values that it takes must occur inside the set 2S. Okay. So now I will use this polynomial to get a bound on the size of S. Consider the following matrix. So let me draw this matrix M. It's going to look like this. The rows of the matrix will be indexed by elements x and t, and the columns y will be indexed by elements of t. This matrix has a feature, and what are the entries? The entry that I'll put here is p of x plus y. So this is a matrix over the finite field F3. Now, the facts written here on the left imply that this matrix is 0 on the off-diagonal entries and non-zero on the diagonal. It's non-zero on the diagonal. That's because P does not vanish whenever you have an element of the type 2z, where z comes from S. P does not vanish, right? And those correspond to the diagonal entries. But if you take x and y that are distinct, and you look at p of x plus y, then it has to vanish, because s plus s is disjoint from 2s. Okay, and all such elements, p has to vanish. And that means the rank of this matrix M, the rank of the matrix here is at least the dimension of V. On the other hand, I'm going to show that this rank can be upper bounded, and that's because the every entry here is obtained by the evaluation of a low degree polynomial. So I can write p of x plus y here. This is the value of every entry of this matrix. That can be expressed as a sum. When I evaluate this polynomial p, which has degree d, on inputs x plus y, every monomial will be a monomial in x times a monomial in y. Okay, so I can write this as a sum over all monomials little m of degree d over 2, degree at most d over 2, m of x times some function f sub m of y plus. Alright, so because the polynomial p has degree at most d, every monomial that you obtain will have degree at most d over 2 in either x or y. And so I can express p of xy like this, where every term has a monomial in either x or y of degree at most d over 2. But now if you think about what's written here, this expression corresponds to expressing the matrix M as a sum of many matrices, namely for each monomial, generate a matrix that corresponds to just the contribution of that monomial here. And for each monomial here, generate a matrix that corresponds to the contribution of just that monomial. Then, if you look at what's written, the monomials that correspond to x here, the matrices that come from a single expression like this, has rank at most 1. Okay. Because all of the columns of the rows are multiples of each other. Okay. So the upshot is the rank of this matrix, I claim, is at most the dimension of p of d over 2 times 2. So now let's put together everything that we've learned. We know that this quantity is bounded by the dimension of v, which is at most the rank of m, which is at most 2 times the dimension of p d over 2. And that implies that the size of s is at most 2 times the dimension of p d over 2 plus 3 to the n minus the dimension of p d. It turns out that the best way to set the parameters is to set d to be equal to 4n over 3. 4n over 3. And then you get that this is 2 times the dimension of p 2n over 3 plus 3 to the n minus the dimension of p 4n over 3. Now, let's reason about what's written here. This quantity here, this is the number of monomials of degree at most 4n over 3. 4n over 3. And this number, 3 to the n minus the dimension, that's the number of monomials of degree greater than 4n over 3. Greater than 4n over 3. And actually I claim that the number of monomials of degree greater than 4n over 3 here is the same as the number of monomials of degree less than 2n over 3. And that's because you can associate to every monomial of degree bigger than 4n over 3 another monomial whose degree is less than 2n over 3 by replacing each variable, each occurrence of xi to the k by xi to the power 2 minus k. Okay, sort of the complementary degree. This will take all the high degree monomials and map them to low degree monomials. And the parameters have been set up, so all the monomials whose degree is greater than 4n over 3 will be mapped to monomials whose degree is less than 2n over 3. So the upshot is that this quantity is actually bounded by 3 times the dimension of p 2n over 3. finally, we just need to estimate this quantity, and to estimate it, let's think about what happens when you sample a uniformly random monomial. What's the chance that that monomial will lie in the set of monomials whose degrees at most 2n/3? Well, if you sample a random monomial, in expectation, each variable will have degree 1, because the degree is either 0, 1, or 2. So the expected degree will be n, and each variable is picking an independently random degree. So the probability that the degree of a random monomial is bounded by 2n/3 is exponentially small in n by the Chernoff bound. And that means the number of such monomials here is bounded by some constant c to the n, where c is less than 3. And that proves exactly what I wanted to prove. I guess this c is not the same as the c that I wrote before, because there's a 3, but if you change c, then you get what I said. So that's the short proof of this last fact, and I hope you appreciate how this really basic question about arithmetic progressions has so many connections to beautiful ideas for mathematics.